In this lecture video, we start looking at multivariate random variables and their distributions. Consider a random experiment with sample space S, and suppose that x1 and x2 are random variables defined on the sample space S. Then the ordered pair containing the two random variables is a bivariate random variable, sometimes called a random vector, with two-dimensional sample space, script A, given by the following. It's the set of all ordered pairs, x1, x2, that result as the elementary event E ranges over the sample space of the original experiment, S. Let x1 and x2 be random variables, each of the discrete type, and consider them jointly via the two-dimensional bivariate random vector, or bivariate random variable, x1, x2. Denote the two-dimensional sample space of this random vector by script A. Suppose there exists a function lowercase f such that the function evaluates to a value that's greater than or equal to 0 for all ordered pairs x1 and x2 in the real plane, and then for all subsets of the sample space of the bivariate random vector, so all events involving the random variable, the random vector, can be obtained, the probability of such event can be obtained by summing this function over the elementary events that comprise that event. Now, if such a function f exists, it's called the joint probability mass function, or joint PMF, of x1 and x2. The CDF of the joint distribution of x1 and x2 is conceptually similar to the CDF of a univariate random variable. We can think of the CDF as a probability accumulator, but whereas for a univariate random variable, the CDF is accumulating probability from a given point on the number line all the way back to minus infinity, which is a one-dimensional set. For a bivariate random variable, the CDF is accumulating probability from a given point in the plane, and then to the left and down graphically, if we're thinking about a two-dimensional graph, to the left and down of that point to minus infinity in both those directions. All right? And so that is how this CDF is defined, for the probability of the CDF evaluated at a point in the plane given by S comma t is defined to be the probability that x1 is less than or equal to the first argument s, and x2 is less than or equal to the second argument t. And this probability can be calculated by summing up the values of the joint PMF for all values of x1 and x2, where x1 is less than or equal to s, and x2 is less than or equal to t. Now, this is the CDF of a bivariate discrete random vector, and hence its domain is R2, which is the entire two-dimensional plane. Now let's look at an example. This is example 44. Consider the experiment of tossing two distinguishable fair dice and recording the up faces. Let x1 and x2 be the minimum and maximum number showing, respectively. And so the question asks us to determine the sample space, script A, of the bivariate random variable x1 and x2, find the joint PMF of x1 and x2, and find the joint CDF of x1 and x2. So let's first determine the sample space, script A, of the bivariate random variables, and then look at finding the joint PMF. Now, the structure of an elementary event for the underlying experiment is represented by an ordered pair, where the first coordinate is the value in die 1, and the second coordinate is the value on die 2. Now, each die can take on the values 1 through 6, and the outcomes of the two dice are independent of each other. And also the assumption here is that the two dice are fair. All right, so we'll use that piece of information in just a second. But the sample space of the underlying experiment, which we'll denote by cap S, is given by this set, the set of all ordered pairs, die 1 and die 2, where die 1 ranges from 1 to 6 and die 2 ranges from 1 to 6. And that generates this set that contains 36 elementary events for the original experiment. Now, let me just point out here that because the two dice are fair, and because the outcomes on the two dice are independent, these 36 possible outcomes are equally likely. So to compute probabilities involving these events, all we would have to do is to count the number of ways that an event of interest can occur, and then divide by 36, which is the total number of elementary events in the sample space. Now the bivariate random variable x1, x2 maps this sample space that we just looked at into the two-dimensional plane as follows. So here we have the random variable, the bivariate random variable x1, x2 being applied to an elementary event from the original sample space S. And the point that it maps into is a point. The first coordinate is the minimum value showing on die 1 and die 2. And the second coordinate is the maximum value showing on the two dice. Now the sample space of this bivariate random variable, which we'll denote it by script A to differentiate it from the sample space of the original experiment S, this sample space contains 21 elementary events and is given by the following set. So script A is given by the set of ordered pairs x1 and x2, where x1 ranges from 1 to 6, and x2 ranges from x1 up to 6. And so that generates this set of 21 elementary events involving the bivariate random variable x1 and x2. So we've got the sample space of the original experiment identified, and let me just again point out that the 36 elementary events in the sample space of the original experiment are equally likely. We also have identified the sample space of the bivariate random vector, but the 21 outcomes in this experiment are not equally likely. Their probabilities are going to depend on the probability structure on the original experiment. So let's take a look at how to compute these probabilities. So in order to be able to fit everything on the page here, let's denote the outcome of die 1 by D1 and the outcome of die 2 by D2. And so for elementary events in the sample space of the bivariate random variable, so for elementary events in script A, note that in general, the probability associated with such an event is going to be given by the probability of the events from the original sample space that get mapped into this event of interest. All right? Now, there are two situations that we need to consider. If the two coordinates are equal, okay, then the probability of such an event is going to be equal to 1 over 36, essentially. And if the event of interest, the elementary event of interest, is such that the first coordinate I is strictly less than j, the second coordinate, then the probability of such an event is going to be equal to 2 over 36. All right, and so take a look back at the sample space of the original experiment and see if you can convince yourself of this fact. As you can see here, there are 2 elementary events from the original sample space that get mapped into this event here, where I is strictly less than j. And for an event ij where I is equal to j, for a given value of I, j, then there is only one elementary event in the original sample space that's going to get mapped into that, so that probability would be 1 over 36. And so based on that, we can come up with the joint PMF of the bivariate random variable, x1, x2. It evaluates to 2 over 36 if we evaluate it at a point where x1 and x2 are both in 1 through 6, but x1 is strictly less than x2. And the PMF evaluates to a value 1 over 36 if x1 and x2 are both in the set 1 through 6, but x1 is equal to x2. And then if we evaluate the PMF at any other point in the plane, then it evaluates to 0. Now note that the way that this PMF is defined, it is defined for all points in the two-dimensional plane. Remember that whenever we define a PMF or a CDF, it has to be defined for all values in the appropriate space for which it's being considered. Now, to come up with the joint CDF, we have to be careful and remember the definition. We are evaluating, when we evaluate the CDF at a given point, we are accumulating the probability over the two-dimensional plane from that point and then to the left and down. All right? And for this kind of example, for a discrete, for a bivariate distribution where the random variables are discrete, it's a little bit cumbersome to write down and perhaps a little bit complicated or tedious to calculate. But for this distribution, there is a fairly nice formula for the joint CDF. And again, remember we have to define the CDF or represent it so that it's defined at every point in the plane. And so the CDF evaluated at a point x1, x2 is going to evaluate to 0 if either x1 is less than 1 or x2 is less than 1. If the point at which we're evaluating the CDF is such that x1 and x2 are greater than or equal to 1 and less than or equal to 6, and x1 is less than or equal to x2, then it evaluates to this expression here in the second line in this piecewise defined function. So now let me just point out before I read this off that this funny-looking notation, which I've got down here at the bottom of the slide, this denotes this is the greatest integer function. So that this function here represents the greatest integer less than or equal to x. So if we were evaluating this if x was 3.5, for example, right here, then this function evaluated at 3.5 would be 3 because 3 is the greatest integer less than or equal to 3.5. Right? If we evaluate this at 4.1, then it evaluates to 4 because, again, 4 is the greatest integer less than or equal to 4.1. So going back up here to the second line in the piecewise defined function, for points which satisfy these two conditions, several conditions in here, then the CDF evaluates to the greatest integer function, evaluated at x1, times the quantity, 2 times the greatest integer function evaluated at x2, minus the greatest integer function at x1. If x1 is greater than or equal to 1 and less than or equal to 6, but x2 is greater than 6, then the expression for the CDF is the greatest integer function evaluated at x1 times the quantity 12 minus the greatest integer function at x1. If x2 is greater than or equal to 1 and less than or equal to 6, and x1 is greater than x2, then the expression for the CDF is equal to the square of the greatest integer function evaluated at x2 divided by 36. And then finally, if both x1 and x2 are at least 6, then we have accumulated all the probability there is to accumulate, and so the CDF evaluates to 1. So again, when we have discrete distributions, the CDF is a little bit tedious to write down in terms of a formula, and it can be somewhat complicated to come up with a formula for that. But this one does have a fairly nice formula. Now, we can simplify the expression for the CDF somewhat, so that we only have, it's still a piecewise function, but we only have two lines here. And so a succinct representation of the CDF is given by the following. So again, if x1 or x2 are less than 1, then the CDF evaluates to 0. On the other hand, if x1 and x2 are both greater than or equal to 1, then the expression for the CDF is given by the following expression. So 2 times the greatest integer function evaluated at A times the greatest integer function evaluated at B minus the square of the greatest integer function evaluated at A all over 36. Now, what are A and B? Well, let's start off by defining B. B is the minimum of x2, the second argument, and this says B, but it should be 6. Let's correct that. All right, so B is the minimum of x2, the second argument, and 6. Once we have B, then A is the minimum of x1 and whatever B is. Now let me show you a few other pages that I've used for working this example. And so let's see here. Okay, so here is a two-way table that when I teach this class in person, I show this up on the overhead screen. I think it helps us to visualize the sample space of the original experiment, and then from here we can construct the sample space of the bivariate random variable x1, x2. But here I've got in this, so this is the experiment rolling two distinguishable fair dice recording the f-faces. And we have the structure of an elementary event, die 1 and die 2, as we said. And so the sample space consists of the 36 elementary events that are in the body of the table. So I've got the outcome of die 1, say the green die, down here, ranges 1 through 6. The outcome of the red die, die 2, again ranging from 1 through 6. And that generates a cell, or a table, with 36 cells. Each cell contains an elementary event for the original experiment. So you can see here that if we get a die, let's see, the die 1 is a 4 and die 2 is a 3, all right, then we're in this cell and that outcome is represented by the ordered pair. All right. Now, another table like this that I use. So let's think about mapping each of these elementary events into the bivariate plane according to the bivariate random variable that we're talking about. So x1 would be the minimum number shown, x2 would be the maximum number shown. And so here is what that looks like. Now, I still have die 1 here on this axis and die 2 on this axis. What I've done is I've applied this transformation according to this bivariate random variable to the 36 possible outcomes in the experiment. And now notice that in some cases the order of the coordinates has changed, has flipped, right? So let me see here. For example, down here, in the original sample space, when die 1 is a 6 and die 2 is a 1, then we have the elementary event 6, 1. But now after we apply the transformation, okay, so these ordered pairs in this sample space are x1 and x2. So, the point 6, 1 got mapped into the point 1, 6. Now notice that there are 2 points that have the value, the point 1, 6. There are 2 cells in this table that have the point 1, 6. This cell and this cell. Likewise, there are 2 elementary events here that the 2 points, 2 places where we get the point 2, 6. One here and one here. And so, for example, if we wanted to determine the probability that x1 and x2, the bivariate random variable, take on the value or the point 1, 6, that would be equal to the probability of this outcome plus the probability of this outcome. And we know that each of those two cells has a probability of 1 over 36, so that would give us a combined probability of 2 over 36. On the other hand, if we wanted the probability that x1 is equal to 3 and x2 is equal to 3, well, if you scan through the table, there's only one place in this table where that happens, and that's right here. And that particular cell has a probability of 1 over 36. Okay? So we can use that information and get a tabular representation for the PMF for the bivariate random variable x1, x2. And so now notice that the axes have changed. Here I have the minimum x1 along this axis, and then on the vertical axis here I've got x2, each ranging from 1 through 6. But notice that for values of x that are greater than x2, those have probability 0 because those are not in the sample space for the bivariate random variable. Okay? So you see here, for each of the cells in this table that correspond to points or outcomes in the sample space of the bivariate random variable, we have probabilities. We have 1 over 36 whenever x1 is equal to x2, and we have 2 over 36 whenever x1 is strictly less than x2. So this is another way to represent the joint PMF for this distribution, and it's convenient and it's acceptable. But let me just say that notice that this is using a tabular representation like this. It's not complete in the sense that we haven't specified anywhere that values or probabilities for points that are not in the sample space have a probability of 0. But that's really in this two-dimensional situation probably a little bit too cumbersome to try to do. So when we're working homework problems, lab assignments, examples or something, and we're dealing with bivariate random variables, if you want to represent the joint PMF as a table like this, that's completely acceptable. That's perfectly acceptable. You don't have to come up with a formula like we came up with in the notes. Likewise, we can represent the joint CDF in terms of a table as well. Okay, and so here is a table for the joint CDF. So again, I have x1 along the horizontal axis here, and then x2 along the vertical axis, each ranging from 1 through 36. And then for every value in the table, or every cell in the table corresponding to a particular combination of x1 and x2, I have accumulated probabilities, values of the CDF, okay, at that particular point. So for example, the CDF evaluated at x1 equal to 2 and x2 equal to 4 would be 12 over 36. The CDF evaluated at x1 equal to 5 and x2 equal to 2 would be 4 over 36. Now make sure that you understand this table. Make sure that you understand how to calculate the values in this table, because again, for these bivariate random variables, when we work these problems in the lab assignments and in examples, specifying the joint CDF using a table like this is going to be perfectly acceptable. I'm not going to require you to come up with some kind of a formula for the CDF. I mean, if you do, that's fine, but I'm not going to require it. Now, let me just, again, say, so going back to the joint PMF, when we evaluate the value of the joint CDF at a particular point. So, for example, let's evaluate the value of the CDF at the point x1 equal to 2 and x2 equal to 3. Okay, right here. So x1 equal to 2, x2 equal to 3. And so what we need to do is accumulate all the probabilities to the left and down from this point. And so we would be accumulating probabilities in this region of the table. So 2 over 36 plus 2 over 36 plus 2 over 36 plus 1 over 36 plus 1 over 36. And so the CDF evaluated at x1 equal to 2 and x2 equal to 3 is 8 over 36. So let me bring that back up. So you see exactly how we got that. Likewise, let's evaluate the joint CDF at the point x1 equal to 4 and x2 equal to 2. All right, so we need to accumulate all probabilities to the left and down from that point. And so we're accumulating probabilities over this region. And so that should equal 4 over 36. And so when we evaluate that, you can see here that that's what we get. So again, it's perfectly acceptable for you to represent the joint PMF and the joint CDF of a bivariate random variable using tables as we've done here. It's not going to be necessary for you to come up with a formula like this. Because in a particular situation, it just may be too difficult. All right? So as long as you know how to make those tables, that's going to be fine.